Yeah, just a minute. Give me a minute. I have to close some of the files. If I opened, unfortunately, it will be a problem. Yeah, now I share the screen. Are you able to see my screen, PPT?
Yes, sir.
Okay, so in the last class we discussed, just recap for 1 minute, then we go for the today topic. The last class we discussed the problem. We discussed the problem with respect to finite life and infinite life of the life of the component, but we considered the completely reversed load. Completely reversed load, finite life design of the component, completely reversed load, infinite life design of the components. And also we discuss when the component is subjected into different level of stresses. Different level of stresses is nothing but the component subjected to, for example, 220 Newton per mm square for up to 80% of total time. For example, next stress level 200 Newton per mm squared for 20% of total time. The third cycle, the compound subjected to, for example, 100 Newton per mm square. During 30 to, for example, 10% of total time of the components. Then based on that, we discussed a couple of problems, how to find out the total number of life cycle, total number of life cycle for the component when the component subjected into different level of stresses. So in the earlier case, we discussed a finite problem and the infinite problem, especially for completely reversed load, right? In completely reversed load, it won't be a sigma mean. Completely reversed load means sigma max, sigma mean, because that is the important information. So today problem, whatever we are going to discuss, once you are understanding that our today discussion will be very easy. So anyway, we move to not just I tell you what we discussed last class. We discussed only this completely reversed load. Completely reversed load. The first half of the cycle, for example, tension. Second half of the cycle, compression. But the amplitudes are same, but only the negative sign. Denominator here. This is the completely compressive. This is completely tensile. Hence, the sigma mean in this case 0 sigma mean. This is sigma mean. Sigma mean we can sigma mean is equal to sigma max plus sigma minimum divided by 2. Hence in this case sigma mean 0. Whatever we discussed in completely reversed load case, the component life design we discussed based on infinite life, finite life. Then sigma means is going to be 0. But now we are going to discuss the further concept. In fluctuating load condition. Fluctuating load condition. What is the component life? With respect to what is the component life in infinite life condition and finite life condition? We are going to discuss while the component subjected into fluctuating load. That's what we are going to discuss today. So in this case, in this case also we are going to, as I told you that the Soderberg and Goodman theory and Garber theory all are in the high cycle fatigue. Okay, high cycle fatigue. First we see this. What is fluctuating loads? Today we are going to discuss this. What is fluctuating load? Right? Any component we cannot expect only completely reversed load. Completely reversed load is only good example. The beam, uniform cross section of the beam when it will be subjected. For example, what we discussed, the fatigue test specimen. That is not uniform cross section beam. even the uniform cross section beam or standard test specimen, fatigue test specimen, when subjected into bending load, right? Then the first off cycle tension, the second off cycle. This is the first off cycle tension, second off cycle going to be compressive, right? That's what we discussed. But we can't say all the components first off cycle tensile, second off cycle compressive like that. I mean, some components may be a pure tensile, maybe a compressive, or combination of this compressive and tensile, combination of the stresses also may be possible acting in the component. So hence we are that's what we are now we are considering fluctuating load or fluctuating stress cycle for designing the component. Here in this case, fluctuating load, I mean, for designing the components. Okay. Now see here. Earlier, what we discussed. Now, in this case, when you are considering fluctuating load case, stress component, right? Stress component. When you are considering fluctuating stress case, the stress cycle, how it will be the stress cycles? We know already, right? This is the, this is now. This is a fluctuating case, right? I mean, here, what is this? Is sigma max, sigma mean. This is not necessary to equal. Sigma max is equal to sigma mean. For completely reversed load only, sigma max is equal to sigma mean. In this case, sigma A stress amplitude and sigma M mean amplitude, mean stress are not equal to 0. Not equal to 0. So in this case, we are going to discuss today a problem. But here, when sigma A is going to be 0, so for example, depends on, the sigma A and sigma mean, the magnitude of sigma A and sigma mean depends upon the maximum and minimum force acting in the particular component. But when we consider the sigma A is 0, then the sigma A is 0. When you consider sigma A is equal to 0, that is purely static load. Purely static load, then we have to go for, as usual, our strength of material concept, what we discuss a static condition, that component design based on SUT or SYT. In this case, when sigma A 0, stress amplitude 0 in fluctuating loading condition, then we have to go for the, in fluctuating condition, now this is under static load condition. Hence, we have to go for the component design based on SYT, a yield strength of the material, or a SUT, ultimate strength of the material. When sigma A is 0, stress amplitude 0. Suppose sigma mean is 0, sigma mean 0. In this case, when sigma mean is 0, then sigma stress amplitude not equal to 0. In this case, we have to design our component based on that. Based on that is endurance limit strength. In this case, what we have to consider? Endurance limit strength. Either you have to consider endurance limit strength SE. In this case, okay. This is the. This is we considered in early problem completely reversed load. But now in this case, we are going to consider this is the concept now. But when we are considering both, the stress and the number of stress cycles are dispersed here and there. Now we move to the our main SN diagram further. Now you can understand. First I close this. See here. Yeah. Now, when we are dealing with the combination of sigma M and sigma A, magnitudes, stress amplitude sigma A and mean stress, then our life cycle, when you are finding the life cycle of the component, this is here and there dispersing, then we have to optimize it in particular way. Hence, that the persons, Soderbergh and Goodman and Gorber, they have found there's some concept that based on that concept, we are realizing that safe design of the components, I mean safe region from the diagram, then we have to follow that region only our design of the component. I mean, for example, these three persons, Gerber and Goodman and Soderbergh, they defined based on their concept, they defined this region of interest, safe region of interest and unsafe region of interest. Because here, earlier it was that, I mean, when the both stresses are acting, sigma m mean stress and this, I mean, stress amplitude sigma a, that in the SN curve, the points are dispersed here and there. Here and there, we can't optimize it. Hence, they have gone through some research, then they might have been done some experimental studies, then they came to this way. This is the behavior of the component, either non-linear or linear. I mean, the guys who found that, I mean, Goodman and Soderbergh, their lines, their behavior, whatever they have found that, I mean, concept, this is a linear behavior that is called under linear theories. But the Gerber the concept is, sorry, Gerber concept is the non-linear behavior. I mean, non-linear theory. This is under, I mean, parabolic curve. But see here, now, I mean, as I told you that in this theory, we are going to use both stress, sigma mean and sigma a. Hence, I am using that one axis as a mean stress in the abscissa. It's nothing but x-axis. I am considering mean stress. Y-axis I am considering as it is earlier what we discussed. I mean, stress amplitude sigma a. Yeah, any doubt? Hello, someone try to talk.
No, sir.
Okay, the sigma a stress amplitude in y-axis ordinate. We are considering sigma a. In the x-axis abscissa, we are considering mean stress, because both stresses are playing in this design. Okay, in this, now the Gerber concept. I mean, first we start from the Soderbergh line. The Soderbergh, we considered the endurance limit, and in the x-axis we considered the maximal limit of the mean stress going to be a yield point stress. Okay, and this guy, when he considered these two stress component with two stress component, then he found the concept is linear variation. Now the person, I mean, Goodman considered, I mean, in the y-axis, I mean, SC, endurance limit of the strength of the material, and he considered in the mean stress it may reach ultimate strength. What will happen? Based on that, he developed the theory. This is a linear line, but when he, I mean, Gerber theory developed, I mean, his concept, he also considered the same point, endurance limit, but he considered, I mean, SUT here. In the same y-axis, x-axis, he considered ultimate strength, but his theory based on this non-linear, but I mean, non-linear curve, it's a parabolic curve. I mean, this may be possible when the material, it's behaves, when the material stress, I mean, we know already the material not only subjected into single stress, the material going to subject in complex stress, right? The material subjected to complex stress, the material may not be a linear variation. The material when will be a non-linear variation, then we can go for this kind of theories. Gerber theory is much suitable, and even Gerber theory is more suitable. We will see in the end of the conclusion. We can understand how Gerber theory is much suitable for this design. Okay, now we are using, I mean, y-axis, I mean, anyway, as per the simple tension test, you know, right? I mean, in the simple tension test, I mean, stress strain curve. In the stress strain curve, this is our elastic region. Sorry. This is proportional limit, elastic limit, then yield point. Maximum we may allow up to yield point. When the material reaches yield point, now I mean, going to start plastic deformation. Hence, we can, that's what most of the time we are considering yield strength, right? Yield strength. Hence, they considered y-axis commonly yield strength of the material. Here x-axis also they consider commonly yield strength of the material. They didn't consider SUT because SUT is always in plastic region. That's what they're considering in, ordinate SUIT, maximum the stress amplitude a sigma SYT, the means is maximum going to be SYT. They consider like this, commonly they consider in both x-axis and y-axis for further defining these theories. So here, so now we know, right? When our stress component, see here that the curve, parabolic curve on the SC on line joining SC and joining SC on the ordinate and joining line at the point SUT on the abscissa, in that nothing but in the x-axis, this parabolic curve, whatever the design component, when the components are non-linear behavior, then we are following this theory. Whatever that failure, whatever the region above this line, then it will be a failure region. Below this line, below this Gerber line, it will be a safe region. Similarly, you can consider when you follow the theory, Goodman lines. When you follow, for example, Goodman lines, above the Goodman lines, failure region. Below the line, Goodman lines is safe region. Similarly, you can consider Soderberg line. But see here, as compared to Gerber theory, then Goodman and Soderberg's are more conservative and more safe region. Okay. Now, the SYT is nothing but this is the SYT. It is also called the limit on first cycle of stress. First cycle of stress means we already know that fatigue life. What is the fatigue life? The material when the component going to first initiation crack, first initiation failure. Before the number of cycles, maybe 10 power 5 cycles. After 10 power cycle, the first cycle when it is going to have failure, before that cycle we are saying that fatigue life, right? Similarly, we are saying that when the material reaches SYT this is the called first cycle of stress. Now we are considering that is what we are considering this SYT as a standard in both y-axis and x-axis for further defining the modified Goodman theory. So before going to modified Goodman theory, now see, understand this here, this equation first, then we go for the modified Goodman theory. Yeah. Now see, now we know, right? These two theories, Goodman theory and Soderberg theory, they've gone through their research, then they came to know that linear theories. In the linear theory, we are using general equation, x by a plus y by b is equal to 1. In the x by a plus y by b is equal to 1. Right? Now, yeah. See, this is, here apply in, first we are considering the Soderberg line. In the Soderberg line, sigma m by SUT. Sigma m, it should be less than the SYT. Yield strength. If you take y-axis, sigma a, sigma a is nothing but our stress amplitude in y-axis. Sigma mean is, we assume that sigma means is in x-axis. Maximum should be sigma SE. We can't go SE, but it should be less than the XE. And based on the straight line theory, here sigma m by SYT plus sigma a by SE must be equal to 1. And hence the ratio must be this ratio, sigma m by SYT must be less than 1. Sigma SYT must be less than 1. Less than 1. This combination, sigma a by SC also must be less than 1, and this summation must be equal to 1. So then sigma m and sigma a always less than the SYT and SC respectively. Now come to the Goodman theory. Now only this is different. I mean, sigma A is a common. Both points are starting from same point. Both theories starting from the ordinate same place. I mean, near to the, I mean, at the endurance limit. But in x-axis, obsessor, this guy, I mean, sort of Goodman line ended with the SUT, ultimate strength. Now, ultimate strength, then this is must be, this ratio must be equal to 1. Then this is, I mean, must be equal to 1. Then the region of interest under, I mean, the safe region. We are our compound region of interest under in safe region now. Now, this is the truth. Now, I mean, we will go for further discussion because SUT are playing. Then how to eliminate the unnecessary regions here? We will discuss now based on that. That we are going to discuss in the modified Goodman theory. Okay. See here, the components. I mean, most of the components subject. Okay. The components which are subjected to fluctuations are designed by the construction of modified Goodman theorem for the purpose of the design problems are classified in two groups. The first one is component subjected to fluctuating axial or bending loads or bending stress. Suppose the component subject, second case we are going to discuss component subjected to fluctuating torsional stresses. First case we discuss now. Okay, I mean, see, now we already considered the maximal limit of stress is nothing but yield strength, SYT in y-axis and SYT in x-axis, right? When you draw SYT in y-axis, I mean SYT in y-axis here and SYT in the x-axis here, obviously it is going to be 45-degree line. I mean 45-degree line. Now this is the region, I mean, where the starting point is B, SE is endurance limit and ending with the SUT, that is nothing but our Goodman line. That is nothing but our Goodman line, right? Now, Goodman line. Now, when we are draw the line CD, the CD line is intersecting at the somewhere point in the Goodman line. I'm assuming that point B. Okay. Now this is our region of a safe region. Now the modified Goodman theory says that this is the region O, A, B, C is the region under safe. This is under. I mean, this is the safe region. I mean, why he came to this concept? Why he came to this concept? Why we discuss now? See, the Goodman is modified by combining the fatigue failure with the fatigue failure with failure by yielding, SYT. Here failure by yielding. I mean, this is line AB says that fatigue failure. The line BC says that yielding. Okay, yielding. The line AB says that fatigue failure. This line. I mean, this line AB says that fatigue failure. The line BC says that our yielding. But when before modification of Goodman theory, what we consider, this is the under, I mean, this is under, I mean, SUT under ultimate strength. This is a plastic region. Then we can't say exactly this is the area under the curve, area under the line here. The area under the line, we can't say that safe region. Still, the material subjected into plastic region. That's what here. That's what here. These are the region is that, I mean, life. What are the, I mean, failure data points are distributed in this region. This is may not be as safe. Hence, based on modified Goodman concept, now this region he came to first, I mean, conclusion. This region O, A, B, C is under safe region. But because this is when the material reaches yield point itself, we are saying first cyclic stress, the material going to have a failure. But when the material crosses SUT, obviously going to have failure. Hence he came to a conclusion OABC is our safe region of interest. Okay, see here in this region, here the line AB is our portion and the AB portion is the what I told. The line AB portion is now AB portion is the fatigue. AB portion is the Goodman line. Goodman line. The line BC portion, the BC is now yield line. Okay, yield line. But when this is coming here, the line, when this region mostly when it will come, sigma mean stress greater than sigma A. This region going to reach this. When our mean stress is greater than amplitude, stress amplitude, during that time we are reaching this region. For example, you can draw the line for B. I can draw the line B. See, especially the yielding region. I can draw the line B here. Now, this is, sorry, okay, you will draw here. Now, this is now our stress amplitude measured from the material experiments. Okay, this is our sigma mean now. Now sigma mean is greater than sigma A. Now this is a Goodman line, but when sigma mean is greater than sigma A, we are going to under yielding as well as under yielding under as well as beyond this region. We are overcoming from the, we are away from the safe region. We are going to away from the safe region. Hence, mostly we are trying to avoid in this situation. Okay, now this is a modified Goodman theory. Now suppose now I draw a line, based on my sigma S, based on my actual condition, I can draw the line from here, 0, then OE line. That line is somewhere intersecting on the Goodman line. I'm not saying exactly draw this line. You may draw like this. You may draw like this based on your stress condition. You may draw like this. Then, but for example, I consider the line OE. When you draw the line X, this is based on your SA, SB, SM. SA is nothing but stress amplitude. S means nothing but your mean stress amplitude. But why we are considering different notation, I come to later. Now see here, I draw a line. First understand this line OX, where it is intersecting. If you take anywhere, gradient, then tan theta is nothing but our maximum stress, sigma A by sigma M. Sigma A by sigma M. This is the stress amplitude. This is the mean stress amplitude. This is nothing but sigma A is nothing but load by area. Area is common. Then finally PA by PM. Now tan is equal to PA by PM. Now I come to later. What is the SA and SM is introduced. You can understand come for later. Now see, similarly, we are assumed that the first case, the component subjected to fluctuating or axial, or bending stress. Now this is a tan theta. I can consider same way when the material component subjected into bending. MBA, this due to amplitude, stress amplitude MBA. This is bending stress amplitude due to mean load. Okay, bending moment with respect to mean load. This is bending moment with respect to stress amplitude. Okay, you can now see here. Now sigma A. If the sigma A is always our applied stress amplitude or measured stress amplitude, sigma A, from the material, from the component. Suppose if my stress amplitude, SA stress amplitude, if I am following using some factor of safety, still I can extend my life of the component. Okay, still suppose sigma A stress amplitude for the component is 100 megapascal. Now if I use as factor of safety, factor of safety sigma A divided by FS, then this is I am considering other notation SA. Now still if I am using this one, now my component is still under this line only. Now my component is under this line only. Which line now? Under this line region only. I don't like to go beyond this line. I don't like to go beyond this. That's what I would like to restrict my sigma M and sigma A. Because as I told you, when the sigma A reaches, for example, I draw another line. I draw another line here, this straight line. My sigma A is here. If you take this is going to be in the plastic region. I would like to avoid that. Hence, I'm introducing the factor of safety here. I mean, sigma SA divided by FS. I mean, the SA and FS always in this region only, AB region only. Similarly, I'm using SM, I'm using factor of safety. SM, I'm using factor of safety. Are you clear now? Now, this is that's what I'm using factor of safety here. This is our good modified Goodman theory. Mean modified Goodman theory while the component subjected into fluctuating axial and fluctuating bending stress. Okay. Now I come to the second theory, which one we discussed now. We told this is second case when the component subjected into fluctuating torsional stress. Fluctuating torsional stress. See, now in the fluctuating torsional stress, the same we are considering. This is, I mean, earlier we used endurance limit strength SE. Here, fluctuating torsional shear, hence I am putting SSE. Here, SSE we already discussed beginning. Okay, SSE is nothing but fluctuating of the component fluctuating torsional stresses. I mean, endurance limit corresponding to fluctuating torsional stresses, SSE. S superscript SE. Okay. Now here SSY. I mean, here earlier we considered SYT, SUTs under tensile, right? Under shear, we are considering SSY. Under shear, we are considering ultimate strength, we are considering under shear, fluctuating shear, torsional shear. Okay, similar thing. Now the same concept I'm using here. This is my what I considered SYT in the earlier diagram. Now I'm considering here. I mean, this is my SSY. SSY. Now draw this two line SSY in the y-axis. What we considered earlier, the similar SSYT used earlier. Now in this case, I'm using SSY. Draw this two line. Then x-axis, y-axis is going to be in 45-degree angle. Now in the y-axis, I'm using here torsional stress amplitude. This is torsional mean stress amplitude. Torsional mean stress amplitude. Now draw this. Now where this intersecting, this is the region of the, that our Goodman line is intersecting this region. Goodman line is intersecting in this region. But what is the mean stress? What is the mean stress here? Now, in the shear stress, torsional shears, flexion torsional shears, we draw the torsional mean stress. We draw the torsional mean stress here. I can draw the torsional mean stress here from the point here. Torsional mean stress. This is my torsional mean stress that is parallel to the now torsional mean stress. This is the torsional mean stress. We draw the torsional mean stress is nothing but the horizontal line because it's not like that tensile or compressive. Torsion stress is not like that cyclic load acting in tensile and compressive. Hence, I'm introducing the straight line here. It's not like that tensile and compressive loads. Hence, I'm introducing straight line. Then, where it is intersecting this straight line, that is the region we are considering the safe region. We are considering the safe region. Now come to this. Similar calculation. Now here, torsional stress here. This is our torsional stress amplitude. Shear stress amplitude, nothing but our SC here. SC here. Now tau max. Tau max. We are summing these tau A. Torsional stress amplitude tau A and torsional mean stress amplitude sigma tau M is nothing but our SSY. This is nothing but our SSY. See here, this is our tau A. This is our this is now our so sigma tau A plus okay, tau M. Now here they are applying the same concept what we discussed earlier. The tau Y must be the tau A if the tau A if less than the SSE, then it will be under the much safe region. Hence, we are introducing Fs in the y-axis. In the shear strength with respect to fluctuating torsional shear. Okay, the endurance limit strength, shear endurance limit strength. Now, similarly, we are introducing, this is now nothing but our tau max also. This is our tau max. But instead of using this full value of SSY, considering full value of SSY, I am using factor of safety. Then the tau max also going to be, then now our tau max going to be restricted within the permissible limit. Then we are under the safe region. Now the Gerber equations, once we discuss this, then we go for the problems. Now the Gerber line, as I told you that early, it's a non-linear behavior. This theory is now under the non-linear theories. Okay, it's non-linear theory, and Goodman and Soderbergh are in linear theory. These are linear theory. Now see here, there are this theory is under a parabolic or elliptical curve instead of straight line, right? Now, hence we are saying that non-linear theories. Now, see here, the points. Here, Goodman theory, the material is in under yielding or ultimate strength. Hence, is a squared. That equation. I am telling this. Now, see here, SA by SE. The Gerber theory obtained based on his concept. SA, this is SA is we know already. SA by SE plus SM divided by SUT. SA is SA by E when this is sigma A. SA is nothing but what is SA? SA we discussed already here. Here. SA is nothing but our sigma A into Fs. Now, he considered SA at axial load condition. Now, SM, in the mean stress amplitude in the x-axis, then SM by SUT whole square, because this is a non-linear theory. But here, why is the considered in the square term here? I tell you only that reason we can understand. Okay, see, the material is under yielding. Or ultimate strength. The material may subjected it under yielding or ultimate strength, right? Ultimate strength during that time, and this is a major concern. This is a major concern because the material going to have a failure in this when the material going to reach, because the theory is, that's what the failure points are distributed here also. Distributed here. See, these are the failure points. The failure points are distributed under this region, under this region, under this region. So based on modified Goodman theory, we restricted up to this region, right? We restricted up to this region in the earlier theory, right? We restricted up to this region. But in Goodman theory, in Gerber theory, we are not applying any modified Gerber theory concept, but only we are discussing about Gerber theory equation. But this is up to this, even our material is somewhat safe condition as compared to ultimate strength. Hence the square term here he is using for this component SM by SUT, where SUT is presented. Okay. Now SA divided by SE plus SM divided by SUT is equal to 1. SM, this is a common for all theories. SM now, SM divided by SA. This is SA. This is SM. But when we are going for Goodman theory, we are using the, we would like to design our stress amplitude from SA divided by Fs, then factor of safety. Then it will not reach beyond this region. It will not reach beyond this region, still in this region only, in this Goodman region only. Then the material, the component under safe limit. But the SA that, directly I am taking this SA for our Gerber theory, SA divided by SE plus, SE is here, SA divided by SE plus SM here SM I am directly taking from SM directly I am taking divided by SUT whole square is equal to 1. Okay, so now I mean when you use Garber theory, your stress amplitude is high. That is true, right? When you use Garber theory, your stress amplitude is high. Then stress amplitude is high. For example, now this SCA. This SCA is stress amplitude high, right? Stress amplitude high. Then when you are designing the component based on this stress amplitude, your dimension of the component going to be more. Then when the dimension of the component more, then if we apply the stress amplitude less than the SCA, the actual practical stress amplitude, when we apply less than SCA, the component life will be more. That's what we are using this Garber theory for defining the dimension of the component. I mean, one more time I repeat here. I mean, when we are using Garber theory, the stress amplitude will be more. When the stress amplitude more, our design of the component, dimension of the component, which component dimension we are defining, the component dimension also going to be more. When the dimension of the component is more, even we are applying the stress component even we are applying the practical stress amplitude, sigma A is less than our SCA, then the component design is much safer than other two theories. But I mean other two theories, but only that I mean Soderbergh theory and Goodman theory is a simple concept. But when we are going for critical components, Garber theory is better. For simple, I mean, based on application, based on criticality, we have to use this. We have to use these theories. When we are going for critical components, better you can choose for Garber theory. Then, but when we are going for moderate application, we have to use this theory. Yeah, please 1 minute. Hello. Okay. Now this is a Goodman theory. I mean Soderbergh theory. I mean Soderbergh theory SA divided by SC plus SM by SUT. The squared term we are using. This is the major part. I mean this is the under plastic region. Hence we are using square term here. So okay, more importance. Now come to this fatigue design under combined loads. Now, I mean combined loads. See, now this is the one of the interesting one. See, one is I mean what we discuss axial or bending. I mean combined load is nothing but axial or bending and torsion. These are we discussed earlier separately. Axial or bending is separate. We discussed separately case 1, and torsion, fluctuating torsion stresses we discussed separately in the earlier case, right? But we cannot expect the component going to be always separate load like axial bending only, or I mean torsional fluctuating stresses like that. It may be combined both. The component may be subjected into combined stresses, right? Then in practical case, very difficult to combine both loads when the components are subjected into combined bending and torsional load, right? Similarly, the bending moment and the torsional moments are leads. I mean also are leads to mean alternative stresses, mean stress as well as alternative stresses. I mean, not only bending stress or torsional fluctuating stress subjected into the component, also the component subjected into torsional moment as well as bending moment, right? So in this case, how to design our component, how to design our stress amplitude or mean stress. That's what we are going to discuss now here. Now see here, I mean. In this problem, we already discussed the theory of failures, right? Theory of failures. What is the theory of failures? There are different theories. One is maximum normal stress theory, maximum shear stress theory. distortion energy theory. It's nothing but one Mises theory, right? See, based on that, here based on the one Mises theory, distortion energy theory. This is, we already know, distortion energy theory. Sigma squared is equal to 1/2 sigma into sigma x minus sigma x minus sigma y whole squared plus sigma y minus sigma z whole squared plus sigma z minus sigma s whole squared plus 6 into tau xy squared plus tau y squared plus tau z squared. I mean, we came from this equation. This equation is obtained using our distortion energy theory. Now, see, now for simple case, now we think about only two-dimensional case. No need to go for three-dimensional case. Now, where sigma x, sigma y, sigma z are normal stress. Okay, normal stress, and tau xy, tau y z, tau z x are, shear stress. Shear stress. Then then if you go for tau xy instead of tau xy, tau yx, if you put, that is complementary shear stress, right? So now these six stress components, these six stress components are independent stress components, and the tau yx, tau zy, tau xz, those are in dependent stress components. But only we are taking these six stress components when we are dealing with the component in three-dimensional stress case. Now, but we are restricting our discussion now into two-dimensional case, biaxial stress case. Then during that time, assuming that sigma z, tau xy, tau xz, tau yz are going to be 0. Tau xz are going, tau yz are going to be 0. Okay. Here they are eliminating the first case, they are avoiding this shear stress component. The second case, they are going, first case we are avoiding this shear stress component. Later case we are going to consider both shear stress. You may ask that, sir, you are saying that tau xy also only biaxial stress component you are saying, then why you are considering tau xy going to be 0? First, I am assuming my component only axial load condition, biaxial load condition. Biaxial load conditions, I draw this. Here, this case only we are assuming this. This case I am only considering. Okay, only axial load acting in the biaxial direction. Then during the time these components are 0, then substitute this equation, you are going to get sigma. This is sigma is nothing but your stress in which the two-dimensional case, stress amplitude in two-dimensional case, finally we came to know that sigma is equal to square root of sigma x squared minus sigma x sigma y plus sigma y squared. This is obtained from the distortion energy theory. Now, the mean and alternating stress of the sigma x is sigma x, mean and alternative stress of the sigma x. Sigma x is one stress, this one, and sigma x, I can write now sigma xm, mean stress component and alternating stress component from sigma x. I can consider sigma xm, sigma xa respectively. Similarly, this sigma y, mean stress component and alternating stress component, I can consider sigma ym, sigma ya, and sigma ya. Okay, because we already know, right? When we considered simple tensile load earlier case, completely reversed load, during that time only one stress, only one bending stress, then we considered sigma a, sigma m, simply we consider. Now two stress components are acting in the component, now in both are in biaxial direction. In this case, now I am splitting, my sigma x going to be a sigma xm, my sigma x going to be a sigma xa. Similarly, my sigma y is going to be a sigma ya, sigma ym, like that. Now you might have been understood, I hope that. Now only with respect to sigma m. Sorry. Only I would like to find out sigma m, mean stress component. Then what are the notation we put to sigma ym and sigma xm? Those things you substitute in this main equation B. Now, when you consider sigma xm, then sigma m is going to be a mean stress component. Then sigma xm squared minus sigma xm, sigma ym plus sigma ym squared. Right? Now, as I told you, this is a simple example. We discussed earlier bending stress. I mean, the subjected into single stress, right? The single stress, result in, we considered sigma amplitude, sigma stress amplitude, mean stress. Similarly, we are using here sigma is subjected into sigma xm, sigma xa. Sigma ys is subjected to sigma ya, sigma ym, like that. Now, only I am considering a mean stress component. Now I am going to consider average stress amplitude sigma A in both the case. Now when I consider sigma x, sigma xa, sigma y from sigma ya from sigma y, then this component I am taking now, these two components I am taking now to find out my sigma stress amplitude. This component I am taking now find out this stress amplitude. Now, right? Now then this is our now sigma stress amplitude while biaxial stress is acting, but in this case we are not considering the CSS component. Okay, now come to this second case, combined bending. Now we move to combined bending and torsional moment. When you are considering combined bending and torsional moment, only now combined bending and torsional moment, now sigma, now you take from the main equation sigma y, sigma z, tau y z, tau z is 0. Then if you substitute, if you consider this component going to be 0, okay, then bending as well as shear is going to be there. Bending, you may consider sigma x. Here I am considering the component sigma x only not equal to 0, but and tau xy not equal to 0. You may consider sigma y not equal to 0, tau yx not equal to 0. But my intention is here to consider both stress component, both axial as well as shear stress component should be presented in my component. So that is combination of both tau sigma axial and tau xy shear. But you may consider like this. But now in this case, now substitute our original equation, distortion energy equation. Finally, you are going to obtain, this is the equation. Finally, you are going to obtain, this is our, stress, this is sigma is equal, this is you are going to obtain. This equation is a function of, now sigma is a function of sigma x, axial condition, and tau xy, torsional shear stress condition. Now, similarly, what I told you here, how I considered m, mean stress, and stress amplitude sigma a, how I considered while biaxial load condition. Similarly, I am introducing same notation here. When my sigma x is acting in the material, now the material is now acting like this. Only tensile and sigma x and tau xy. Now in this case, now with respect to sigma x, I can write sigma xm, sigma xa. When I am considering tau ix, that also we already discussed tau torsional, tau a, tau m. The last discussion, tau a, tau m. Similarly, I am introducing the same tau xym, tau xym, tau xya. Then only you take m component, mean stress component, substitute this, now this equation, substitute this equation, then this is your mean stress component when the component is subjected to both tensile and tensile or bending and torsional shear. Only when I'm considering a, stress amplitude a, this is our equation. This is stress amplitude when the component subjected into tensile or bending or tensile or bending or sorry, tensile and bending and tau external torsional shear all are combined here. Now this is the concept. Now we discuss the problem. Do you have time? Yeah, tell me by any doubt. Okay, at least one problem we discuss. Remaining 4 problems are there. It won't take more time. We will discuss in next class. Only one problem we discuss now. Okay. Then we move to close the today's discussion. I mean, just to see this problem. I mean, a cantilever beam made of cold steel, cold drawn steel. Now I'm considering infinite life problem, fluctuating load. Earlier we discussed completely reversed load. Now, I mean, the cantilever beam, I mean, made of cold drawn steel, 40 C8. I mean, it means the ultimate sense 600 Newton mm squared, yield strength 380 Newton per mm squared, shown in figure, see here. Now this is the force acting. This is a fluctuating loading, minus 50 Newton to 150 Newton fluctuating loading. The expected reliability is 90% of the life. Okay, I mean, reliability factor given, reliability life is given. We have to find out the reliability factor corresponding 90% from the table what we discussed earlier. The factor of safety is given 2. The notch sensitivity factor is given 0.9 K. Notch sensitivity factor, sorry, Q. Determine the dimension of the diameter of the beam. Now the clear diagram is given here. The load is fluctuating load minus 50 to 150 Newton. SUT given, SYT given. I mean, our reliability time is given, life is given, 90% given, then FS given, Q is 0.9. Then, I mean, these are easy. SE is SE. And this is SE standard based on standard test specimen. We already know 0.5 times SUT. Then SUT given, find out 300 Newton per mm squared. I mean, with respect to this, we can consider, we can find out our, I mean, Ka. What is Ka? Surface finish factor, Ka 0.77. I mean, we are assuming the component here, they have given D is not given. We are assuming that 7.250 mm within this region. Hence, my size factor is 0.85. I mean, this is now my reliability factor based on 90% from the table we can obtain. Okay. Now, R by D ratio. This is a fillet is given 0.2 D, and R by D ratio we know now the radius is given 1.5 D. Okay. And the capital D is given 1.5 D. This is D, small d is given D, right? Now this is the smaller radius is D. Then we know, right? R by D ratio is given 0.2. Then D by D, small capital D by D, small d ratio is given 1.5. Then from this relation we go back whatever we discussed earlier chart. We obtain the stress concentration factor. Now, I mean, once we know that, we can find out the fatigue concentration factor, I mean fatigue stress concentration factor Kf. Okay, this is 1.396. Now Kd is a modified factor, now 1 by Kf, right? Now this is our actual specimen's endurance limit, SE. Substitute all the values in this formula, you are going to get this. Up to this we discussed similar problem we discussed earlier. Now this is important thing. Now see here, construction of modified Goodman diagram. I mean, we know bending moment to maximum, bending moment minimum. Based on this load we can find it out. I mean, here also we have to find out mean bending moment. I mean amplitude, bending moment, amplitude of the bending moment, stress amplitude. Here bending moment amplitude. Okay, mean bending moment MB max, MB mean divided by 2. Bending stress amplitude, similar thing, stress amplitude here MB max minus MB mean divided by 2. From this we are able to find out MBM, mean bending moment. This is amplitude of bending moment, we can find it out. Then now this is theory we already discussed, right? Now this is the theory when this is theta, this is SA, this is SM. Yeah, here it is there. I mean SM, this is SA. I mean SA here we do not know that SA. We are going to find out SA. Our aim is to find out SA only. Please give or cooperate just 2 minutes. I finish it. Okay. SA is here. What is SA? We don't know. Okay. SA and SM, we do not know that. We would like to find out SA and SM only. Now tan A given based on bending moment, bending stress, bending amplitude of bending moment, mean bending moment, we can find it out. See here, this is, we already discussed sigma A by sigma M. This is nothing but, I mean, the bending stress with respect to the bending moment with respect to sigma A, bending stress with respect to sigma M. That's okay. Now see here, I mean, this is our, I mean, this is our, I mean, modified Goodman diagram. Now, the line equation line AB, this is AB, right? AB, I mean, SA divided by SA, here SA divided by 120.126.116, because now SA, we know, right, this line one is our Goodman line, modified Goodman line, right? Modified Goodman line. So based on the concept we are discussing here, SA divided by SA divided by 126.11, we already got it. SE here, SE, this is nothing but SE plus, I mean, SM divided by SYT, ultimate sum. This is one, this is the equation we already discussed, right? Now substitute here. Now this is one equation, SA, I mean, SE we know, SE we know, endurance limit of the component, actual endurance limit of the component we discussed based on size factor, based on surface finish factor, based on, I mean, sense modified factor. Now we know this is, we can consider one equation. Now another equation, tan theta, we have found it based on bending moment. Now that is same, SA divided by SM. Now you may ask that, sir, sigma A by sigma M. I mean, put sigma A. SA is nothing but sigma. SA is nothing but sigma A into Fs, right? SM is nothing but sigma M into sigma S. I mean Fs. Sorry, Fs. Sigma N into Fs. Then, I mean, even tan theta is equal to, I can consider SA by SM. This Fs is going to be cancelled. Okay. Then when you are using here, going to be cancelled. Then sigma A by sigma M will come. Instead of sigma A, sigma M, I'm considering SM. Now, this is second equation. Then to solve this two, simply with these two equations, A and B, finally you are going to get SA and SM. Now, this is SA and SM. What is our sigma A, sigma M must be less than that. Then only we are within this region, right? Now use factor of safety to find out our sigma A, actual component subjected into sigma A, the component subjected, actual component subjected into sigma A, then SA divided by Fs, I mean SA divided by Fs. Now SA divided by Fs, we know, right? SA is nothing but, I mean, which one is the maximum bending stress here? This is the maximum, 10,000 Newton millimeter. That information I'm going to consider here for finding my, I mean, sigma A. Sigma A is equal to SA divided by Fs. The left hand side, I'm introducing my maximum bending moment. Based on that, I'm going to find out. Now, finally, I can find it out. Here already know SA is, we know SA divided by S is our sigma A, right? But directly we don't know sigma. Our aim is to find out the diameter of the shaft. Hence, I'm introducing the sigma A in terms of bending moment. The sigma A I would like to introduce in the way of bending moment. That must be right hand side. That must be this. Hence, I'm introducing the bending moment value to find out my dimension of the shaft. Then introduce here 32 into 10,000 divided by d cube. This is nothing but M by Z, right? Then right side is, we know sigma A, SA we know, Fs we know. Finally, our diameter of the shaft is 12.13 mm. Sorry guys, because next class we will complete the remaining problems and we go for the next chapter. Tomorrow, sure, we are going to start the next chapter. Now, I come to home screen if you have any doubt. Yeah. Any doubt? Yeah, please. If you have any doubt, please go ahead. Yeah. Do you have any doubt?